So we're at the last unit in this course. It's called Revolutions in Modern Physics. So it's really two parts. It's about the special theory of relativity is the first part, and then we talk about quantum mechanics and modern physics in the second part. So the first here, the special theory of relativity. This is section 11.1 in your textbook, and we're going to go back all the way to the start of the course and really talk about inertia and frames of reference, because I need to make sure that you have a firm understanding of that in order to understand what happens in this part of the unit specifically. So on this slide it says, at the turn of the 20th century, many scientists felt that they were close to a complete understanding of the physical world. And this is actually, it's really interesting, because at this time it almost felt like they've solved every problem. They knew how the laws of motion worked. They could understand motion in the larger sense, the macro sense. The understanding of electricity and magnetism was becoming firm, and they determined that there was a connection between the two. They also determined that light is actually a form of electromagnetic radiation. So all of this started to look like the field of physics was going to be solved. But then things got a bit interesting when we started to look at the more microscopic world. And this is when things kind of started to fall apart. So I guess this slide just goes on a little bit to explain about the idea that electricity and magnetism are related. So they knew about how light propagates through a vacuum as well. So now it says, at this time only a few questions remained. The nature of the atom was still unclear. Physicists had observed that light emitted from perfect radiators called black bodies did not behave as predicted. The phenomena by which metals gave up electrons under certain kinds of light also had physicists mystified. Moreover, contrary to Maxwell's assumptions that all electromagnetic waves, like all waves, needed a medium, there was no evidence to support this. So, actually, this was a little bit before they had the idea that electromagnetic waves can self-propagate. It was also the idea of light being emitted from black bodies was unclear as well, and we'll get into that a bit later. And another thing we'll get into later in the second part of this unit, the phenomena by which metals gave up certain electrons. So certain metals, if you shined light at them, electrons would be ejected off of those metals. But how that would happen was unclear, since light typically doesn't cause particles, matter, to move, and in this case light was actually giving energy to an electron and causing the electron to move. So how that happened was not clear either. So with these problems, the idea was that they were probably going to solve these based on the current understanding, the current framework of physics. But every time they tried to solve these problems using the models that were available to them, things were not coming clear. They weren't able to solve this based on their understanding of physics, and this was Newtonian mechanics and Maxwell's EM waves equations and other understandings that were available at the time. So new models needed to be created, and there were some who kind of felt that the new models weren't necessary because the current models should be fine. But one of the main contributors of these newer models was Albert Einstein. And on the note on this slide, it says that Einstein's ideas in physics changed our perspective of space and time. And that is very true. So we'll get into that a bit later as well. But he's a famous physicist because he changed physics as a whole. So now it says, recall from earlier chapters that a frame of reference is a coordinate system that you can use to observe and describe motion. Any frame of reference that is at rest or moves with a constant velocity is an inertial frame of reference. And within an inertial frame of reference, Newton's laws apply whether there is movement or not. So now we'll go back to Unit 1 from this course. And even on your formula sheet, if you recall, it says that those 5 laws of motion that we use, acceleration needs to be constant. That means that our frame of reference is inertial. If we have a frame of reference that is not moving, that has an acceleration of 0, or we have a frame of reference that has a constant acceleration, it's easy to calculate what's happening in terms of how velocities change, how distance can be determined based on velocities. So that having an inertial frame of reference is easy for the math, so much so that in cases where we don't have an inertial frame of reference, we often alter our questions so that we do have an inertial frame of reference. But what we weren't considering was what happens when we are observing something from varying frames of reference. So what I'd like you to copy down is the definition for frame of reference. Even if you have this copied down previously, I want you to copy it down for this unit, and the definition for inertial frame of reference. And the short form for frame of reference, which you can use when you're writing up any questions in this course, is capital FOR, frame of reference. So let's look at a question here. It says, suppose you're inside a windowless railway car. So you're in this railway car, and there's a billiard table at the center of the car. This question says, while rolling a cue ball forward, you notice that the ball slows down suddenly, even though you have not applied a backward force on the ball. Explain the motion of the ball in terms of inertial and non-inertial frames of reference. So if you roll a ball on a billiard table, it will keep rolling until it hits the back rail. However, if a force is applied to it, it will either move faster or move slower, or it will move in a different direction. So if this ball is moving forward and all of a sudden you see it start to move backward or slow down, rather not moving backwards, so it starts to slow down, that means a backward force must have been applied to it. And in absence of a force that you can see being applied to it, that force could be due to a change in acceleration. So in this case, the train changes its acceleration. It starts accelerating forward, which causes a backward force on everything that is inside that frame of reference. And that's what's causing the ball to slow down. Next it says, this cue ball is rolled forward, and then you notice that the ball moves to the right. So in this case, the change, the acceleration must be to the left. So an acceleration to the left causes an inertial force that acts on the ball to the right. That's our proof as well that this is a non-inertial frame of reference, because there is nothing that's acting on that ball aside from the inertial force. Another question here, it says, do Newton's laws remain unchanged for an observer in different inertial frames? And they do. It only changes the way in which the motion of the object appears to the first observer. So now what we're going to get into is we can still use Newton's laws in different frames of reference. But if we're looking at an observer from one frame of reference, at an observer in another frame of reference, or at a phenomena in another frame of reference, then the way Newton's laws change for that observer, it will appear different for that observer. So let's look at this situation, and this has gone through in your textbook as well, starting on page 575. But we have an observer who's standing on a little railway car, We're going to call this reference frame 1, and he throws a ball up and down in the air. Now, if that railway car is stationary, that ball will go up and down, and observer 1 will see it kind of rise and fall at the same point where he dropped it. If that railway car is moving with a constant acceleration, the same thing will happen. This happens when you're in a car and you flip a coin. If you flip a coin and you're traveling at a constant velocity, the coin will fall up and down at the same location where you flipped the coin. But if the car, while the coin is in the air, if the car slows down or speeds up, the coin will move. It will move backward if you speed up, and it will move forward if you slow down, because of the change in the frame of reference is no longer inertial. Now let's add another observer, a stationary observer. So this woman here is on the who is not on the railway car. She's watching the person on the railway car, and as that person throws the ball up, for that observer, of course, the ball goes up and down in the same location. But if that railway car was moving at a constant velocity, observer 2 would see a parabolic arc showing the motion of the ball. As the ball moves, it has a velocity equal to v, which is the same v that is the velocity of the cart, as well as its velocity that the observer or observer 1 would have given it when he threw it up and down. So you can copy down the principle of relativity. It's at the bottom of the page, but it says, once corrected then, by considering the velocities of the two reference frames, the physical results become the same for both frames of reference. This situation provides the basis for the principle of relativity. For all inertial frames of reference, the laws of Newtonian mechanics are the same. The main idea of the principle of relativity has a long history going back to at least the work of Galileo in the 1600s. This is sometimes referred to as classical relativity. So this type of relativity was known, and it was easily demonstrated and predicted. We actually used this classical relativity when we were doing Unit 2 in order to calculate the elastic collisions, where we would have to make a velocity equal to 0 by artificially, I guess, kind of adding a velocity to both of our initial velocities. If you remember those elastic collision equations, we could only use them when our velocity, our final velocity was 0, or sorry, not our final, but our other object's velocity was 0. So what changes things is actually the speed of light. Now you may know that now that the speed of light is a constant value, but at the time that wasn't known. So for 200 years, physicists knew that Newton's laws of motion remain the same in all inertial frames. However, electromagnetic waves seem to be different. As it was then understood, Maxwell's theory stated that the speed of light with respect to the ether, this was still when we had the idea that ether was this fluid that exists around around all the planets, was always 3.0 times 10 to the 8 meters per second. This meant that if you were at rest and observed a light source move relative to the ether, you would measure the speed of light to be different from c, depending on where you were standing. So once they knew that there was a limit to the speed of light, what physicists didn't consider was, what does this limit mean in terms of frames of reference? So Albert Einstein started to come up with thought experiments to kind of explain what would happen, and he used this kind of railway car example, and he used light. So here's an example of that. It says, when the railway car below is at rest, the speed of light from the flashlight is in both directions is c. So we have a railway car at rest with a flashlight on it, and the light moves to the left at a speed of c, and moves to the right at a speed of c. Now when we start to move that railway car. It starts traveling at v. What happens is we would assume that for an observer at the front of the railway car, the light would be moving at c plus v to that observer, and he would see the light moving back at c minus v. But c is a limit. We can't go faster than c. So c plus v would have to be equal to c. That's what we're going to get to in this. So experimental evidence did not support the idea that the speed of light varied with the speed of the inertial frame. So an experiment to try to measure this is one that's kind of shown here. This was performed by Michelson and Morley. They tried to detect the ether, and that showed no change in the speed of light with the motion of the Earth. So they were not able to see a change in the speed of light. You don't really need to know this experiment. You should just mainly know that Michelson and Morley, they were able to determine that the ether was not present. They were also able to determine that, or they were able to confirm that there was no way to travel faster than the speed of light. Ultimately, the results of these and similar experiments suggested that electromagnetic waves do not require a medium in which to propagate, and that the existence of ether could not be proven experimentally. This implied that the speed of light, and in fact all members of the electromagnetic spectrum, through a vacuum should be seen as being the same as in any inertial frame of reference. So that was the speed of light principle, and I'd like you to copy that down. The speed of light principle is the speed of light through a vacuum should be seen as being the same in any inertial frame of reference. So if it's the same in every inertial frame of reference, that means your c plus v, of course, is equal to c, because you can't really add to that c. So given the unsatisfactory consequence of classical electromagnetism, as well as the lack of evidence for the ether, Einstein proposed two postulates that were based on the principle of relativity and the speed of light principle. Now these don't sound very spectacular, but I'll read them both, and then we'll talk about how they work in conjunction. So his first postulate, which you should copy down, is that the laws of physics are the same in all inertial frames of reference. No physics experiments can ever determine whether you are at rest or moving at a constant velocity. Okay, so that's the first one. That's the principle of relativity. The second postulate is the speed of light principle. There is at least one inertial frame of reference in which, for an observer at rest, in this frame of reference, the speed of light c in a vacuum is independent of the motion of the source of light. And that's the second. That's the speed of light principle. So regardless of how fast the light is moving towards this person, this observer, the speed of light will remain the same. And you can copy down the special theory of relativity in green, but I'll just read a little bit before that. So when we consider those two postulates together, it gives us an entirely new understanding about the universe. So the understanding is that the speed of light must be constant and the same in all inertial frames of reference, because the laws of physics do not prefer one frame of reference over another. So that basically, this gives us the idea that the speed of light is a maximum. We cannot go faster than that. And what we then had to do is figure out what are the effects of this. And before we go into those effects, I'll just read out the special theory of relativity as it's written here. It says, all physical laws are the same in all inertial frames of reference, and the speed of light is independent of the motion of the light source or its observer in all frames of reference. So let's look at, actually this is something you can copy down as well if you like how it's written here. The laws of physics are all the same, and the speed of light is independent of the motion of the light source or its observer. So that's the special theory of relativity. All observers who measure the speed of light will find it has the same value of c, is what that means. So the first statement had been accepted since the time of Galileo and Newton. The second statement was a radical departure from the common understanding of the basics of physics. It took scientists a long time to accept it. Eventually it was accepted, and the special theory of relativity is now considered to be one of the principal scientific triumphs of the 20th century. So here's some simple thought questions. Let's say there's an astronaut in a rocket, and he's moving at half the speed of light along the Earth's surface. And he shines a light forward from the rocket. So this guy's moving at 0.5 of c, and there's a light shining from the rocket. So according to the astronaut, the speed of light is c. And according to somebody on the Earth's surface, the speed of light is also c. It's not traveling any faster than c. So that doesn't seem too spectacular, but we'll get into this in our next lecture of what this means in terms of how this changes physics. So if we are using Newton's laws of motion, and our velocity is constant regardless of the motion of our frame of reference, that starts to have some very interesting effects on things such as time and mass. Here's another question. You're traveling in a spacecraft without windows. You're also far from any planets or stars. Determine an experiment that you can perform to determine whether you are at rest or moving at a constant velocity. So if you're traveling at a constant velocity, or if you are at rest, there would be no way of knowing the difference. This is the same idea as if you're on Earth. Consider Earth as a spacecraft in a way, because it travels through space. We can't really tell that Earth is moving from our own understanding. If you're locked in a room on Earth, you can't tell if the Earth is moving. If you're in a spacecraft and it is moving at a constant velocity, and you try that coin flip idea, the coin will go up and down at the same spot in which you initially flipped it. So there's no experiment you can perform without being able to observe anything moving around you outside of the space station or spacecraft. You wouldn't be able to determine that. Now, the other part of this question says, is there an experiment you can perform to determine whether you are in an inertial or in a non-inertial frame of reference? And here you can. If you put, say, a ball in the center of the room, and you make it so that that ball is as stationary as possible, if you are in an inertial, a non-inertial frame of reference, an acceleration of that frame of reference will cause that ball to move. It will either move forward, backward, left, or right, depending on where the acceleration is occurring. So this is really just a kind of a thinking lecture. We've sort of finished it. Try the questions at the end of this lecture. I want you to have a firm understanding of this before we start getting into some of the effects of the special theory of relativity on Newton's equations. Now that we have this idea that there is a speed of light limit, and when we're moving close towards that speed of light limit, some strange things will happen.